Hold on, not this one. Hang on. I start off with the MCQ first. This one here? Okay. Right. So it's a frictionless surface at P, rebounds inelastically, and then comes to rest momentarily at Q as it moves from the Q. Okay, all right. So what's gonna happen here first? Like the first part here. What's gonna happen here? It's gonna accelerate. Actually, you know what? All the options are the same, right? All the options are the same. You know that it accelerates. It accelerates, so the velocity goes like this. But I'm not too sure why you talk about KE. Oh, because of the inelastic. So the K and the GP is less, right? And then it becomes constant speed. Hits the wall. Technically, it's supposed to be a very, very steep line, not vertical, not perfectly vertical. Constant speed again, and then decelerates again, right? Coming to rest. So, sorry, your job is actually to figure out the time taken, actually. Time taken. Yeah. Oh boy. It's not so much of like it's not so much of the basic shape. The basic shape are all the same. I say it's a very close call between A and B then. Yeah. Yeah. A and B. So B's the answer, right? Yeah, B's the answer. Okay. So between A and B, A is wrong because you cannot have something that's steeper here and this one here like this, right? They must have the same acceleration, right? These two parts here, because these two slopes are going up the slope, going down the slope and going up the slope. You get what I'm saying, right? I think the big question is, what's the acceleration along the slope? How much is that? Not 9.81. 9.81 is only for vertical dropping objects. So along the slope, g sine theta. I mean, this is just in case, right? You get another question. Right, so if it's a frictionless, but this is only true for frictionless surfaces. This is only true for frictionless surfaces, right? Yeah. So then you can say it's g sine theta and all that, but yeah, you can't. Yeah. So so A can't be it, right? Let's say we compare between B and C. All right. Let's say we compare between B and C. Now D can't be it because velocity time graph, area displacement, you will notice that D, right, has the exact same displacement here and here, which can't be the answer because it does not go back up to its original height. It collects inelastically, right? So the distance traveled is less, right? So I'm looking between B and C now, right? So we have to go by elimination. There's actually no real way of actually proving that the graph will exactly look like this. Yeah, understand? Okay. So the reason why C can't be it is because the time taken for the flat ground is pretty much the same, right? The flat portion, when the ball is going along this flat portion, right? So option C shows us the same. Now option C fits the other two criteria. They have the same gradient here and here. Okay, there's a bigger distance traveled first part, smaller distance traveled second part. Okay. Actually B also is a bit off though, I feel. Look at the distance, like this distance so long. You know what I mean? You know what I mean? Like but I don't have numbers, I can't really tell. Like I would say that in this situation, unfortunately, like the best answer is still B. You know what I mean? For C, right, the only reason why I rejected C even though it fits all the criteria, is because the time taken on the flat surface, right, going down towards and going away, right, it's the same, which doesn't make sense because it's supposed to be traveling at a slower speed, and therefore it should take longer, right, for the flat surface, right, the flat surface. So therefore it should take longer. Yeah. So B is correct, right, because it does show that it takes longer, but this looks unnaturally long. So much that this area here is like I can't really ascertain whether this area is like more or less than this one here. But I mean B is still the best answer in that sense. Okay. Which year is this? RI 2022. Okay. Common test. Okay, that's fine. Okay, that's okay. This one here? No, can we move on to the next one? Can okay. This one? Alright. Huh? Okay. So I do sense, because from all the questions you sent so far, right? I do sense that it's a kind of like a case where you have trouble with forces and multiple objects. And it's usually a problem that comes like that's carried on from secondary school, right? And knowing the other two, I think when they joined me only in year 4, right? So but you can sense that Sube and Shruti had like a lot of like prior misconceptions before then, right? They had like a lot of force problems. They had issues with understanding forces. So I'm not too sure whether it's a school thing. It might be, I don't know. Okay. So we have multiple objects here. So what I want you to learn how to do is this. You have to be able to look at the big picture. That means you group them all up together. Or you can select, right? You can select which one you want to look at. You want to look at C, you want to look at B, you want to look at A, or you want to look at combination of AB, or you want to look at combination of BC. Also can, right? But if you cannot look at the combination of AC, that makes no sense. Right? Like immediate objects, yes, can. Alright? So let's look at the whole picture first. Let's look at the whole thing first. Okay, let's look at the whole thing first. And then I'm gonna ask you a couple of questions. And look at the force. This force, right? This applied force is acting on which object? It's like acting on object A, correct? Okay. So yeah, but just remember that force F does not act exclusively on B or C, right? The whole thing, yes, you can consider the whole thing or you can consider A with regards to force F. Okay? Can Right. So block A experiences a resistive force F from the surface during this acceleration. What is the magnitude of frictional force between blocks A and B? Right? So I think one thing is to understand that sorry. One thing is to understand that there is friction between like surfaces A and B, there's friction between surfaces B and C. Okay? But there is no there is no like kind of like a I mean there is friction now, but we there's not enough information at this point in time. So we need to figure this out. So you got force here, you got friction here. I think the key word is this word here. Accelerated. What do you understand about that? So can we write F minus F equals to now 3 identical blocks, I'm going to discuss 3M A. Right? Yeah. Do you understand why is this like that? You understand, huh? Okay, good. So that is if you look at the whole picture. Okay? Now you have to decide what you want to look at now, because they did ask you, right? A experiences a resistive force from the surface during this acceleration, right? And then they ask you, no, so this frictional force is from the floor, right? They did from the surface, okay? And they ask you what is the friction between A and B, okay? Between A and B. So now they want to ask you about the friction between A and B. Do you understand that the friction between A and B, right? You see this statement here, the friction between A and B. Do you understand that this actually means that there are two forces, right? There's one friction force that points on the bottom of B by A, right? This is F on B by A. Okay, never heard of this before, right? Or not entirely sure. Sorry, what? Yeah, it's friction, friction. Okay, so I mean, if let's say you don't want to use capital, right? Oh, you're asking me whether is it this friction? Ain't no way, no. This is I'm gonna label this as yeah, yeah. Nope. So do you understand that when you walk forwards, friction points forwards? That's because your foot is moving backwards, right? So friction is opposing your foot's motion, but it's also helping. If you look at the free body diagram, it's actually pointing in the same direction as your movement. So get rid of that idea of friction opposes motion, right? That is a common trap that students fall into. Friction can cause motion too, which contradicts whatever you thought of, right? Friction opposing motion. Hang on, hang on. No, slowly. Because your issue now is not about your issue now is not about like the answer to this thing. Right? You need to understand the underlying concepts. I can easily just tell you, then like that, like this, you will still not get it. Right? This is for your long game. Alright? You must also understand there is also a friction acting on B by B on A backwards, like this. Because if B is gonna is gonna get a friction from A, then there will be a friction by B on A. And it's acting on the opposite direction. Hang on, So the question now is, how do we know that friction acting on B is pointing forwards and not pointing backwards? You know what I'm saying? Right. The simplest way to see this for yourself, okay? Let's see the objects on your table. You put your phone on that booklet over there. Okay, you put the phone on the booklet over there. I'm going to do the same as well. I got a book here. And I put my phone on it. Like that, right? Then I'm going to pull the book. Why does the phone follow? What? Why does the... How come I'm pulling the book, right? I'm literally pulling the book. The phone is not stuck on it. It's just sitting on top. Okay? I pull the book fast. Is the phone accelerating also? Together with the book? Why? What's causing the phone to accelerate with the book? Friction. And where's that friction pointing? Forwards. It has to be pointing forwards. So if you isolate B, there must be a frictional force, right, by the bottom object. So this force F is not acting on B, right? It's the friction below, right? So one more time, So if you really need to remind yourself this, right, in the exam hall, right? You put your calculator on top, you take a piece of paper and you pull it like that. Then you think about it yourself. There is a friction acting forwards on the object that's stacked on top, that's causing them to move together. Is this friction? Right? When I wrote this equation, F minus F equals to 3ma, I was grouping all three objects together. Right? But this thing here, right? So what happens is that I am only, if you wanted to isolate A, you technically would have to draw this force as well. Yeah, right? If you isolate A, you need to look at A only, right? A has this force pushing on it, right? There's a frictional force by the surface, and there's a frictional force by B, right? That would be the acceleration, the same acceleration of A. But if you look at three objects, then it's F minus F equals to 3ma. So it really depends on what you want to look at. Okay? So for now, I don't really know what the answer is. I actually don't really know what the answer is. I'm gonna leave these two forces here. I'm gonna tell this, right? Like I say again, you can choose what you want to group. You can group B and C together. Okay, you can group B and C together. If I group B and C together, what is the force that causes both of them to accelerate this way? So when I isolate B and C, what force causes these two objects to accelerate together with the whole thing? This friction, right? It will be this friction. So and I mean, honestly speaking, that's exactly what they're asking for, right? Okay, so if that's the case, I can write down another equation. I can write down friction by A on B, right, is equals to, right, 2ma. There's no other opposing force acting on B and C together, right? So if you group up B and C together, there's no other forces acting on it. There's only one force, which is this one here, right? Fa, the friction that's acting on the underside. Now you cannot isolate B. You cannot isolate B because if you do that, then you need to consider of the friction by C on B, right? So what I'll do is, for convenience, I'll just group up these two. You can if you want to, but you're just introducing another unknown, right? Okay, so now I have two equations. I don't know whether this is enough, right? This is the first time I'm doing this question. I'm just showing you how I work through the process, right? Then I start looking at the options. Look at the options. They didn't mention M anywhere. So based on the equations, right, I would probably need to get rid of M in a way, but I'll be left with F and F. That's okay. Some options give me F, some options give me F, some options give me F and F, right? So what I want to do is I want to sub the M out, if I can, and make this guy the subject, right? If you want, you can make M the subject here. You can make M the subject here, right? And then you just sub M inside here. I'm pretty sure. Oh, but there's a A. You need to get rid of A as well. No, it'll be gotten rid of, right? If you make M the subject here, and you sub it inside here, the A will disappear because you bring the A down, you multiply here, A times A is gone. I believe this is the answer. Right? The way I look at it is this is the answer, right? Yeah, so this is your answer. This is the first method. I'll show you another method. Okay? The next method is to isolate A. Let's say we isolate A. Right? Let's say we isolate A. This is A. Right? Let's look at all the forces acting on A. Right? Let's look at all the forces acting on A. So legit, there's a force acting on A force. There's a friction force here, right? And then there is that force by B on A. Okay? Now, if you end up finding this, right? Is that still the answer? That's still the answer, right? It's action-reaction pair, right? That's totally fine. Okay? So if you look at option A, so now we write an equation for object A. So F minus F equals to, now A is only one object, so M times A, like that. Oh, sorry, F minus FB, sorry about that. I forgot about that. F minus FBA equals to single MA, like this, yeah. We good? Can? All right. So if you make this the subject, make this subject because that's what you're trying to find, you realize that you need to get rid of the M as well. You need to get rid of the A as well. So then we come back to this one here, right? Maybe we can sub in MA into this, right? MA is will be F minus F. So no matter what, you still have to look at the big picture. End up with the same answer. Do you see that? Right, so if you take MA as a subject and you sub it inside here, you make FBA the subject, you end up with the exact same answer. Two times of F minus F divided by 3. Same answer. Okay, yeah, do it and see for yourself, man. Then you'll know what I'm talking about. But I'll be honest with you, you have to rush through this, so you you try to do it as fast as you can. Got it? Yeah, exact same answer. Okay. Then we have this one here, is it? What's the magnitude of the acceleration of the forces? Okay. So this kind of thing, slopes, check whether there's friction, no friction, smooth surface, right? Wheel, no friction, no problem, okay? And you got 30 degrees, you got 60 degrees. And the way I look at these things here looks a bit wonky, right? There's no friction. Why do you put small f here? Right? Okay. So one thing I noticed is not very confident in the drawing of the forces, right? I see your pencil markings here. Is it because of your scan or what? Yeah? Is it because of the scan? Like, not very confident. Not sure where your arrows are pointing as well, but okay, that's fine. So yeah, okay, good. So straight away, right? Draw the arrows. Right? There's tension here. There's tension here as well. All right. And honestly speaking, you don't have to draw the other components. Yeah, sure. There's the normal, and then there's the cosine theta. There's the normal and the cosine theta, right? We don't need to care about that, right? So we just look at all these. There's no friction, so get rid of all the frictional forces. Don't need to draw the weights and all that kind of things. Okay, good, right? So this is mg sine theta. Always down the slope is mg sine theta. Are you aware of that? You're aware of that. So 3g sine 30 degrees, okay, 3g sine 30 degrees, right, 3g sine 30 degrees, and this one is 1.4 g sine 60 degrees, right? So in a way, right, if you need to decide where is it accelerating to, you sort of like have to compare these two forces. If this is more, then the whole system will go this way. If this is more, then the whole system will go this way. Now I can't eyeball which one is more, right? So I would suggest that you compare, you calculate it out and compare. It's not too long, maybe like 5-10 seconds, right? Punch it out. See what? Okay, that one's stronger, right? What this means is that your object will both your objects will accelerate this way, right? And it will accelerate this way. And they will have the exact same acceleration, correct or not? Why? No, because they are moving, they're connected. They're not moving they move with the same speed. They will have the same acceleration, but the reason why they have the same acceleration is because they're connected. If one accelerates more than the other, then either the string becomes slack or the string breaks. Okay? Now, will the tension be the same? Have I drawn the tension directions correctly? The tension for this object is pointing up. The tension for this object is pointing up. They're absolutely correct. Okay? So you got to always remember that strings cannot push objects. If you draw the tension pointing down, you're telling me that the string is pushing the block down. That makes no sense. Okay? The string is hanging from this string. Sorry, the object is hanging from the string. So the object is kind of like the object pulls the string, yes, but I'm asking what's the direction of force by the string on the object. Right? Therefore it's pointing up. And this one's pointing up. Okay? But this object is accelerating downwards this way, this object is accelerating upwards that way. Which also means that the tension, the value of the tension is somewhere in between these two values. It is lesser than this, but it is more than that. Okay? And the next thing you need to remember that even though the tensions are pointing, in this way and that way, because you got to make sense of where the tensions are pointing, they are the same amount of tension, like the value of tension is the same on both sides. All right, so remember, because tomorrow is exam anyway, so one string, one tension. One string, one tension. Like for the same string, they have the same tension. Okay? Then you can start writing your equation now. So what's the equation you write for this object here? 3g sine 30 degrees minus t equals to 3a. Then what would you write for this one here? T minus 1.4g sine 60 degrees equals to 1.4a. Right? And then solve for I don't know, solve for a. Yeah? You don't have to solve for t, so what you can do is you can take this equation plus the equation, right? And then you can get you can get rid of t already. Okay, next one. Which one of the examples is not, right? Huh? Oh, you don't need this one, you just scan the whole paper. Okay. Is it this one? Huh? This one, huh? Okay. So, tap is turned on and water level rises while the stream remains taut. How would the length of the spring and tension of the string change? Okay? Yeah. So it was already previously submerged, right? And then they added more water, right? That's what's happening here, right? You added more water in. Okay? At least that's how I understand what they're doing. Right? Then they ask you, how will the length of the spring and the tension in the string change? Tension in the string change. So length of spring will decrease lah, right? The spring is inside here, right? You add more water, pressure is higher, it will press down on the spring more, right? So it will be compressed more. Okay? But what will happen to the string itself? Well, I mean, there's only two options, either increase or decrease. So it definitely cannot be no change. Okay. Oh, it should be tighter. Should it be tighter? Wait, I mean, oh no, it should be less tight. So tension is less. Okay, so the reason is when you compress this thing, it becomes a smaller region, right? So now the water filled up this area already, right? Just as assume that it got pressed down, right? Which also means that the amount of water displaced is less. So your upthrust becomes less volume. So the upthrust becomes less. So the upthrust was like previously like this, right? Was this much, but then now the upthrust is only like this much. So there's less upthrust now. Okay? So then you have to look at the container as a whole. You have to look at the container of this. You have to look at this container as an object. What were the things that prevented the object from floating to the top? Right? There's air, right? It would have floated to the top. The things that were preventing it from floating upwards was its weight. Number one, there's the weight, and then there's the tension as well of the string, and the tension of the string is pulling it down. Right? Okay. So if you previously had a lot of upthrust, then the tension here would have been very strong, right? But since now there's less upthrust, right? There's less upthrust, right? There's less volume, water displaced, right? Because water filled up this container space, right? Filled up this container space. So amount of water displaced is less, upthrust is less. So then the tension will be less. Does that work? Yeah? There we go. Right, so tension will be less here. Okay, next one. This one here. So maximum allowable tension is 30 newtons. 30 newtons. Oh, why you use energy here? Oh, sorry. Okay. Okay. So 30 newtons, right? Okay. So you see, my method of solving this kind of questions is similar to before. Which object you want to look at? You can isolate the lift, the crate on its own. You can isolate the present, or you can look at the whole thing. So since the tension maximum allowable is 30 newtons, I'm going to look at the whole thing first. Right? 30 newtons. Okay, 30 newtons. So based on that, based on this 30 newtons, maximum 30 newtons, and the entire weight of the entire system, that means weight plus present, right? Weight plus present, weight of the crate plus the present. What's the total weight here? 2.3 times 9.81, how much is that? Just punch it in. 22.56. 22.56. Okay? So what you have is a total weight of 22.56, right? With a maximum allowable 30 newtons. In fact, you can already find out what's the maximum acceleration of the entire system. Right? Yeah, we find the maximum acceleration first. Max A. Okay? I know the question is what's the force that the present exerts on the crate. But we'll do that later, right? What's the maximum acceleration first? So 30 minus 22.56, then divided by the total mass of 2.3 kg. Right? So what's your maximum allowable acceleration here? It looks like you done something here. Right? So it's what? 3.2, is it 3? 339 meters per second squared. Upwards. Right? Mean is upwards. Right? That's the maximum allowable tension, allowable acceleration before the rope breaks. If you try to accelerate more than this, let's say you try to accelerate at 4, right? In order to accelerate at 4, you need more tension, right? So the thing is that's not possible. Because if you try to do that, you pull it up really hard, right? The thing will snap. Okay? So now you have to look at the present. Now we isolate the present. Now we look at the present itself, right? So I isolate the present, right? Down here, this is the present, right? Then we ask ourselves, what are the forces acting on the present? N by, yeah. So there's a normal contact force by the crate upwards, and then there's the weight, right? Downwards like this. Knowing that the maximum allowable acceleration of this entire system is 3.2339, the question is, how much will the normal contact force be? Now, beginners, like, the Sec 3, Sec 4 students usually will ask me, why is N not equals to mg? That's because the object is accelerating. If N is equal to mg, then it's at constant speed or at rest, right? So for this particular case here, you need to recognize that the N force is bigger than the mg. So we write an equation for the crate, right, which is N minus mg equals to ma, sorry, for the present, not the crate. We don't know what the N is, so N is equals to ma plus mg, right? But this N is for the present. The mass here is the present's mass. So that's like 0.3 times that A, which is 3.2339, right? And then plus 0.3 times 9.81, right? That will be the normal contact force by the present, on the present by the crate, right? You calculate that one out first. And then the last step is to just recognize that if they ask you what's the force that the present exerts on the crate, then it will be the same N value there, because that's N prime. Right? That's the action-reaction pair that they're asking for. Okay? Question, is there another way to do this? Right? Yes, there is. You isolate the crate. Right? So another way of doing this is to isolate the crate. Running out of colors to use. Let's try using blue. Okay, so we isolate the crate. So if you isolate the crate, you know what? I'm going to just use a blank piece of paper. Okay, so if you isolate the crate, like that, then we draw all the forces acting on the crate. There's the tension, right? Because the tension acts on the crate, doesn't act on the present. The tension, and the maximum tension is what? 40, right? 30 newtons. Then there's the weight of the crate, which is how much? 2 kilograms. So 2 times 9.1. 2 times 9.1. And then don't forget, since you isolated the crate, you need to add in the force that the present acts on the crate. So which is that normal contact force. That's the M prime that we were looking at. N prime. You get what I'm saying? Yeah? So how should I write an equation for this if I want to find N prime? Now, of all the forces, which one's the biggest? Yeah, it still has to be this 30 newtons, right? Because it has to be big enough to overcome this and this to help the crate accelerate upwards. But notice how I ignore the present, right? But the present is still inside. It's just that, it's in the form of this force. So when you isolate the crate, right, this is how the forces look like. Right? So what's the equation? 30 minus 2 times 9.81 minus N prime equals to MA. But the mass here is the mass of the crate. right? So that's the 2 kg mass. So 2 times A. Okay, and then make n prime the subject. You should be able to find it. The A we've gotten just now from 3.2339. Is that right? Yeah. We good? Can? Okay. So this will be for that question, right? Few ways to do it. This one don't need. Okay, can. This one? This one also don't need. This one need. Okay, can. This one here is quite an annoying question, right? Once you learn it, you will know. Okay. You drew friction. How do you know there was friction? It's at rest. There must be friction. Otherwise, it won't be able to rest on the slope, right? Okay, there must be friction. You drew mg, but I think you somehow also forgot to draw normal contact force. Did you forget to draw normal contact force? Huh? No. They're asking you to find the force that the slope exerts on the block. That's not what you're looking for. I mean, for whatever it's worth, right? I think we should just draw the normal contact force, right? The normal contact force here like this. It's the normal contact force. Understand? Can? But this question is asking you for the force that the slope exerts on the block, right? So what kind of force is this? Okay, so this force famously is always the total contact force, right? The total contact force. Do you understand? Okay, right. The total contact force being so we have to decide lah. So normal contact force, right, is by what on what? By the slope on the box. Frictional force is by what on what? No, by the slope on the block. You see, right, when you're drawing forces, right, when you're drawing forces, you have to always remember, right, what are the forces acting on him, not by him. So this frictional force, you reckon that it's helping this block to balance and not slide down the slope. This force is by the slope on the box. So you would notice that, the normal contact force is by the slope. The frictional force is by the slope. So this is what they're looking for. The combination of the normal and the frictional force. Okay, so that's it. You probably have to oh yeah. These answer. So it looks very unnerving, right? Because it looks like normal contact force, but this is not normal contact force. This is basically the normal contact force and the friction combined. Yeah. This is the normal contact force and the friction like added together. So their resultant is like that. Yeah. Yes. Why can't it be C? I mean, what happens if the friction is more? Right? I mean, it contributes more of this direction force, and then the vertical force is like that. I mean, looks legit, right? Why would there be a resultant force? Because don't forget, the weight still acts downwards on it. So the idea here is the normal contact force and the friction, they act in such a way that it balances the weight of the object. And the weight of the object is pointing vertically downwards. So when this happens, when you look at it this way for option D, right, you realize, oh, okay, yeah, it's balanced, right? So it can't be C because the weight will act this way, and you have a combined force of the normal and the friction, which points like somewhere upwards like this. This is going to be very weird because this actually means that the block will start sliding upwards, which can't be the case, right? Okay, so D is your answer. Now, then A looks similar as well, right? A actually points vertically upwards, all right? And then weight points this way, right? So why can't it be the case like this? But why does it have to pass through the center of gravity? I mean, it's not a rule, you know? Not quite right. Okay, well, I'll tell you this. If it acts sideways away from the center of gravity and the only other force is the weight, right? Yeah, there will be moments. There'll be anti-clockwise moments. So that's not gonna happen, right? So D's answer because it needs to balance in in line. No resultant force, no resultant torque. Right, so D is your answer. Okay, good. What's the next one? Oh, okay. So this one here. Okay, so you got object P and you got object Q, and they are traveling this way, right? Okay. Is there a force acting on them now? There's only weight and normal force. Like, is there like this? Oh, in the same force. Sorry. I thought this is a collision. I thought they're gonna collide. Okay, if the same force acts on each other for the same duration though. They didn't say same distance, right? Same duration. Yeah, same duration. Okay, same duration. So object P on this surface, object Q on this surface, right? Object P on this surface and object Q on this surface for the same duration. So they apply the force, right? I'm just going to draw an arrow that's connecting to the objects, right? Because forces are supposed to connect. So same force, and same duration. Actually, what happens then? Same force, same duration means what? Means same what? They gain the same amount of. No. Velocity, no. Momentum. Why though? What does F times delta T give you? What's that? Yeah, that's impulse, right? That's impulse, and that's basically change in momentum. So both objects will gain the same amount of momentum, right? So object P and object Q, right, will have the same momentum. They will have the same mv. But the problem is that P is smaller mass, so it's m, right? And then it will be like what? mv, right? Like this. Okay, for example. How about Q? Q will have 2m, but in order to get the same momentum, then the v that Q gets will be half v, right? Half v like this. Yeah, there you go. Right, and then on top of that, they want you to like talk about the gain in Ke by P. That means the gain in Ke by P, right, over the Ke by Q. Is there a shortcut to connect the kinetic energy to momentum? Is there a formula for that? Ke equals to P squared over 2m. So this is one of the equations that a lot of students always forget. Ke equals to P squared over 2m, right? So if you have the momentum of the object, you can square it and then divide it by its mass times 2. Then that's the Ke, right? So if you do that, then you will get mv squared over 2m for P, and then you have the ratio of yes, because inverse of an inverse fraction. Sorry, yeah, my brain just lagged for a bit there. Okay, yeah, there we go. So this will be for question 8. Yeah, tension. Okay. Tension. Well, the only thing I can do is to compare between C and D though, right? Between C and D. Okay, not like exactly a very fair question though, to be honest. Yeah. between C and D, right? Hmm. Right. What's the difference between option C and D? C tells us that the tension reaches mg. That means when it goes past equilibrium, T goes to mg. And then D tells us that the tension is much bigger than mg. Right? You understand? Okay. So firstly, we need to explore the idea. Is it possible? Is it even possible for tension to be more than mg passing through the equilibrium? Yeah, it is, right? Yeah, it's very much like circular motion. But then in SHM, we learned that the T can be equals to mg, right? Like, because it passes through equilibrium. So it's very hard to tell which one is the correct answer though, to be honest. Let's see. How about for option D? Option D, some of the parts actually do go below mg also. No choice. This one D is the best answer. So in real life, right? Not ideal, in real life, the mg will be more, the T will be more than mg. Right? Yeah. So even though we try to, you know the deal with pendulum. Pendulum is an approximated SHM. It's not a true SHM, right? It's approximated because the arc length might not be completely horizontal. Okay, if it's horizontal, then we can treat it as SHM, right? But because it's always an arc length, so in a way, right, it's always circular motion. It's always part of a circular motion. So D is the best answer for this. There's no other explanation for this. Yeah, yeah. Okay, next one. You need this one. You want to try it out on your own again? Right. This one will be like based on the looking at big picture, small picture, that sort of thing. Drawing the forces and writing the equation on both sides. Okay. Now you get three objects, so you probably have to write like three different equations, or maybe you just need one or two. I don't know. Okay. Um, hang on, cause no matter what, I got another guy coming in about like 20, 15, 20 more minutes. Okay. So you try that one on your own. What's the next one you want me to go through? So the forces one was my most concern because, like, I can sense that you are not aware, but maybe you try to pick on what I just said. Right, later on at 7 o'clock, if you need some more help, you just come, you just drop me a message and let me know. But I can't stay too late. I gotta go home. Okay? What's the next one? This one? This one here? Okay. Ooh. Oh, this is hard, man. Okay. So wait, where do you get this from? Where are you getting this idea from? Oh, okay. So you have no idea where it came from? Yeah, it's from G Fields. G fields. Yeah, it's pretty much like correct lah. So I tell you what, there are actually two regions where you learn this, right? Two areas where you learn this. Number one, you actually learn this from work energy power, which is probably the reason why the question number is like 7, and then it's like why are they asking about G fields already so soon, right? Yeah. So this is technically a work energy power. There is a rule. There is a rule here. Okay. The rule is this: if your object, right, if your object is in a field, okay, is in a field, right, and let's say you apply a force such that it opposes the field. Let's say the field is pointing downwards like this. Okay. Let's say it's pointing downwards like this, and you apply a force. If you apply a force that's opposing the field direction, and you actually in fact cause it to move, right? You cause it to move against the direction of the field, right? If you apply a force and cause the object to move against the direction of the field, its potential energy will increase. That's like GPE, right? You have an object in a gravitational field, you move it against the gravitational field, it will gain GPE. Of course, the force must be greater than the gravitational force lah. Okay so far? Can ah? But what happens if you apply a force or you let the object go in the direction of the field? Then it will lose potential energy. So you see the first two part, gain and gain. Right? So that means that the force applied on the object is opposite of the field's direction, which then we will usually take it as negative. Right? Which is kind of confusing because, right, what you don't see here is that this is actually not a G field, this is actually an electric field. Right? Because the further and further I go, right, you realize this, the further and further I go, right, at some point I'm going against the field, and then at some point I'm going towards the field. So it's like, huh? How come I go one direction, but then I'm going against the field, and then afterwards I'm going towards the field again, right? That's because it's based on electric charges. So you won't really fully understand this concept until later on, right? But then we just take it that if you increase potential energy, your force should be negative. Well, A and B are very close, right? And then if you go in the direction of the field, in a positive direction, then you will lose potential energy. So I think A should be the answer, I believe. Is A the answer? A's answer? Yeah, there we go. Right, A's answer. Yeah, so yeah. And it's a constant force, but like what you're saying, actually, because then this one here is in G fields, right? Which is true. So gravitational force is potential energy gradient. So if the gradient is a constant gradient, then the force is constant, which is why A is your, I mean A or B is your answer. Yeah, it's very close, man. Like you can sort of like still argue that B is the answer also, but yeah. But it's about the direction of the field. So down here, this force is considered to be negative because it's acting in the opposite direction of the field. Yeah. Okay, can I mean, this one here, no choice. This one is a bit unfair because sort of like you need to understand E fields a bit better first, then you can do this one. Some of the earlier questions, right? Some of these questions here, sometimes they incorporate later chapters. Which if you haven't done it yet, then you might be lost on you. So, but I mean, don't fret about this kind of questions. It's rare lah. Right? Try to get the ones that you can get. Next one, this one. What's X? And then later on they say that certain change causes Y, is it? Okay. So it cannot be less damping, like what you said, right? It cannot be less damping. Because less damping would mean that it will X first, right? Then Y, right? Okay. Right. So like less damping would mean that your graph should look like this. Less damping, it should look like that. No. The resonant frequency should go higher, and then the peak should be sharper as well. So it should go somewhere like this. Somewhere like that. Yeah. But it's not, right? Well, oh yeah, the answer is A. Yeah, sorry, I just saw the answer. Yeah, the answer is A. This one is really quite annoying. So there's actually two effects. When you decrease the mass, right? When you decrease the mass, the frequency of oscillations gets less, right? Like, oh no, gets more. Sorry, frequency oscillation. That means you hang a light mass versus hanging a heavier mass. A heavier mass will oscillate slower. A lighter mass will oscillate faster. Yeah, there is, but it's like technically not in syllabus. So yeah, are you supposed to know? I don't know. In my class, I made them memorize it. So for spring mass system, T equals to 2 pi square root m over k. Right. So if you decrease the mass, the period will decrease, which means that you have a higher frequency. Okay. Can? So smaller mass, right? Smaller mass, higher frequency, right? Therefore, your graph all shifts towards the right side. You see that they all shift towards the right side. But do you also notice that? It looks like damping has increased? Right? The peak is broader, the amplitude is lesser. You know, like looks like increased damping, right? Okay, which is true also because if you use a smaller mass, it's more susceptible to the resistive forces. Like a heavy mass versus, like let's say you think about a heavy mass, a golf ball versus a ping pong ball. Which one is more susceptible to air resistance? A ping pong ball, right? So that's what's happening here. So you use a lighter mass, you end up in like you end up allowing it to be more affected by resistive forces. So therefore, it looks like it's more damping. So two things happening lah. Okay, so A is the best answer. Uh-huh. No, amplitude of the driving oscillator increases. If that increases, then it should have been higher, right? So the amplitude would have been higher. So C can't be. And it will be exact same shape also. Like they will be exactly on top of each other like that. That will be C. Okay? Right? Yeah. Next one. This one here? Sorry, which one? C triple I, is it? Determine the work done by the normal contact force on the man during the first 5 seconds. Sorry, I have no idea what's happening to this guy. What's happening? Oh, so he's in the lift. He's in the lift. And where is he? Where is it at? During the first 5 seconds, is it? During the first 5 seconds? Alright, so what's happening in the first 5 seconds? Oh, he's experiencing acceleration, right? So he's at rest. Okay. Right. Okay. Alright. Acceleration. Okay. Okay. So this is a change of acceleration, is it? And then this one here is yourself drawn for the velocity time graph of the whole thing. And they ask you what's the work done by the normal contact force, right? Work done by the normal contact force. Okay. Work done by the normal contact force. You know what's the worst thing? The worst thing is that the normal contact force is not constant. Right. The normal contact force is not constant. The normal contact force is equals to the weight at first. Then this is more than the weight. This is even more than the weight. This is even more than the weight. And this is like the maximum normal contact force acting on the man. So the man, right, the normal contact force is like this, then like that, then like that, then like this. So if you want to use force times distance, which force are you going to use? That's tough, right? Yeah, that's tough. What I suggest you do instead, if they ask you a work done, is you have to be a bit flexible sometimes. You have to think about whether or not do you think you can use normal contact force. You know, yeah, I don't think so. I don't think you can use normal contact force because the normal contact force keeps changing. I suppose you can use average normal contact force, but I wouldn't recommend that because it's not very intuitive. I think I recommend you this other method. Okay, work done on the man, right? What does the man gain? Work done over time, right? What did they work? What's the total work done, right? Sorry, work done on the man. What does the man gain? The man gains KE and GPE. So if you can calculate his final KE and you can calculate his final GPE after the 5 seconds, you will get the total answer. But I think, unfortunately, I think, right, I'm more concerned about finding the, I mean, KE can find very easily. You can find area under the graph here, you can find the total velocity, right? Then you can half mv squared, that one no problem. But how about the height though? How about the height? Oh, the height will be hard to find there. Because you can't use Suvet. Acceleration keeps changing. Oh, really? Do you understand that what you did there was an approximation? Right? I think you should write it down by approximation on a graph. Okay? Because that's not a legit equation, right? And when you say by approximation, you understand that what you have just done is you drew a straight line like a triangle. The parts below and the parts above should be equal to each other. Correct? And therefore you can approximate it to be half times 5 times 5. Okay? Okay, yeah? Yeah. So, oh yeah, KE and GP. Right, yeah, there you go. Yeah, you shouldn't do that. Yeah, you should just use the energy method. Okay, it's also something that I think is a bit obscure. Not too sure why as well. A lot of students over the years they also have this problem. What's this next one? Part B, is it? This one here? Oh, part B. This one. Determine a magnitude with respect to the glass wall. Okay, of the reaction force R exerted on the rope by the pole. So it should look something like this. Yeah. Right. But you probably have to sum everything up lah. Oh, isn't it just 1,000 here, 1,000 there, 1,000 here, 1,000 there? So your pole is now the intersection, right? Your pole is now the intersection, is the point where, all right? So, I mean, you imagine your arm is there, right? The rope is over your arm like that. You will feel some force pulling by the lion, and then you'll feel some force being pulled by the zookeeper. You know what I mean? You know? So basically it's facing these two ways. What you got an answer for that one? So what you can do is you can imagine a rope, right? You put a bottle here like this, and then you imagine a rope that's being pulled, like, you know, looped around, and then you pull both sides. So the bottle will feel forces from both sides, like this, right? And therefore it'll go in the middle. That's the idea why. Okay, then okay, this one, no issues. Okay, good. Then this one here, 21A. Sorry, for which one? Sorry, I okay. Are they asking for first minimum? So they block one slit, right? And then you have one single slit. You got the distance. You have, right? Okay. Why can't you use the equation? You cannot use the equation sine theta equals to lambda over b. No, so we have two equations, right? For single slit, this single slit, single slit, you have sine theta equals to lambda over b, and then tangent theta equals to x over d. I think from the lambda and the b, you can find the theta, and then you sub in the theta into the x over d, you can find the distance of the first. What do you mean by you cannot? I think you can. What? Sorry, I don't understand. That's exactly what I just said. So I don't know what formula are you using. Sorry. X equals to n lambda d over a. Do you realize that this is double slit? That's the equation for double slit. This single slit. So you have all the slit stuff confused. This single slit, they block one slit. There's only one slit. Single slit is that one there. Did you think that there was no sine or tangent? Is that what you are asking? The sine and tangent are always there. It's just that if the angle is small enough in radians, it will approximate itself to theta. So most of the times I'll tell my students, right, play it safe, put the sine inside and the tangent inside, but keep your calculator in radian mode. Right, and all your thetas will be in radians. You get it? Right? Yeah. So you need to be able to distinguish the things here. Now what I can do is I can send you a superposition revision that I did with my JC tools, which is maybe like a crash course to remind them of all the separate equations for all the different scenarios. Right? It's not the same. Right? It's not the same. It looks similar, but it's not exactly the same. You can argue that in the end, if you put down the same values, you will get the answer anyway, right? True? Yeah, true. But it's not safe. Besides, what do you think A is? Is it slit separation or is it slit width? Yeah. So that's double slit. Double slit uses slit separation. B is slit width. So B is this one here, 0.15 mm. A is this one here. If you sub this into that one there, you end up with the double slit equation again. So sorry, what? You thought single slit was what? What? Yeah lah, that's what I'm trying to tell you. That's what I'm trying to tell you. I'm telling you that you got the formulas mixed up. So, you have to fix that problem. It's a very, very common problem of superposition, right? So I suggest try not to, you thought it was like that, you thought it was like this, because I guarantee you, right, I think the way that they taught it in school is confirmed damn messy one. Yeah. Okay? To really master superposition, you need to remember exactly what equations there are for each of them. There's actually only four scenarios. Okay? Single slit, double slit, diffraction grating, and then you have this other one, this special one called modulated double slit, which is going to be the case here. Right? All the other things are small little details. Like for example, when do we put sine theta? When do we put tangent theta? When do we take it out? The safe option is always leave it in. Right? And then the next thing is this. Okay, if you're doing single slit, right, lambda over b, what does the theta represent? The angle is from where to where? From the central max to the first minimum. That's for single slit. Right? And nothing else matters. for single slit. Like the second maximum or the first maximum, nobody cares about that. This data is specifically for single slit calculated from central max to first minimum only, which is why the question is asking you for the distance of central max to first minimum. If you use this equation and you sub in the slit separation A, you sub in lambda and D, and you sub in N as 1, for example, what does this X help you find? What is the X there? That will be the separation between central max and first maximum, the next maximum, right? This one is for single slit. So you have to go and be very, very thorough with the details, and that's what they're testing you on. They're testing you on the details. If you mess up the details, then nothing will get to you. Okay, huh? Did I not send you superposition? I haven't sent you superposition yet. Okay, so you might have to quickly churn out some superposition. So you see, you remove the obstacle, then it becomes double slit. Then when it becomes double slit, then this is legit. You don't even have to put the N, because this X here, right, for double slit, right, ideal double slit, the separation is all the same. Yeah? Okay, so that's the fringe separation. Then this is modulated double slit. That's good. That means you know something about this. Okay? That's because the slit separation is 3 times that of the slit width. 3 times. Okay? Which means that the fourth, no, the third peak should be missing one. One of the peaks should be missing. I believe it should be the third one. Yeah, 4515, right? 4515 is 3, right? So the third maxima should be missing. Yes, the third maxima should be missing, right? So you should see a pattern that sort of looks like this, right? You got your central max, then your first, second, and then third should be a blank, and then you go back to the fifth one again, a fourth one again. So this n equals to 0, n equals to 1, n equals to 2, blank, n equals to 4. Right? And that's because it's the envelope. The envelope is wrapping, like, touching the third. The single slit maxima is coinciding with the third maxima of the double slit. Okay, huh? Alright. So maybe just single slit only. What's the next question? This one here? Approximate position of point P, label it with letter P. And they ask you, determine the ratio of S1 and S2. Ratio is what, 1.15, is it? Intensity, is it? 1.15. Okay, then they want you to find the approximate position, is it? Wait, on which figure? On figure 21.2. 21.2, that means here. Okay. So ratio of intensities is 1.15. You figured this out already? Okay. Wait, hang on. No, you did write something here. You said 14 and 15 here. This is the amplitude, right? Amplitude, Oh, 15 over 14. What's the total amplitude of P then? 28. Right? 28. Or rather, no, you know what? Maybe we can just use this one. 1.15. 1.15. Okay. 1.15 plus 1 squared. What do you get for that? Eh? No. Cannot. I cannot do that. Oh man. Okay, that's super annoying. Let me think about this first. What's the original intensity from each of them? Original amplitude. Hmm. Okay. Um, this is really annoying because like I haven't read the question yet, and then I don't have the full picture. And point P is somewhere around here, right? So I'm gonna tell you that one of them is 15, the other one is 14. Point P, what's the total amplitude? The total amplitude is 28, right? 28. If let's say you had a 30 squared and a 28 squared, yeah, let's say it's full squared. I mean that's yeah, because like they say intensity away from this and intensity away from that, right? But then to find P, point P will be like a constructive between 14 and 15. So what is this ratio? What is this ratio? 28 squared over 30 squared. Where's what is that? 0.87, right? 0.87. Okay. Then point P, right? According to, let's say this is the maxima, right? Point P will be 0.87 of that maxima. 0.87 of the intensity. So you find out where point P is, 0.87 of this height here, like that. Okay? Can? Okay, I don't have time to go through the rest of it. Yeah, I either go through later. Yes? Oh, yeah, I actually have to see him now. Can I pass him to you later? Can I pass him to you later? Okay, no, because I need to see him actually. Yeah. Sorry. Okay? Can? Do you know why it's done like that? Okay, so basically, right, you have to remember that superposition is about the adding of the amplitudes, right? So if one amplitude is 14, the other one is 15, then the total amplitude, sorry, the total amplitude is what's wrong with me, is 29. Sorry about that, 29. 29, okay? So it's 29 squared over 30 squared, right? So how much is that? Not 28, sorry. You come in, sit down first. What's that? 0.934. Yeah, sorry. Then you have to go and look for the 0.934. Away, like fraction of the 0.934. You come in and sit down first. So what we are doing here is basically trying to find the ratio of the intensity from the maxima, and the maxima being 30 squared. I'm just assuming there's 30 squared. I'm not too sure what the exact answer is. What did they say?